Hey guys, so in this video I'm going to talk more about bases, how we've talked about them before, but right now I want to start by reviewing some things about bases in in section 2 with the black with the black, white, hard, soft stuff. Um, so what I have here is I have the kind of diagram that we drew at the beginning of section 2 to explain the Stern-Gerlach experiment, and that's how we got our basic concept of a Hilbert space. And so what I have here is I have color axes in blue and hardness axes in orange, and hopefully you're familiar with this. And now what I want to show you is refresh you on how we can write some state vector in terms of in the color basis and the hardness basis. And so what I have here is I've written the white unit vector, or the white state vector is a superposition of being soft and hard, and the black state vector is a superposition of being soft and hard, and similarly the soft and hard state vectors as the superposition of being white and black. And so now, if I have state vector psi that is, say, and I'll write this in blue in the color basis, has some CW, the white unit vector, right, state vector, they're ket vectors, plus C black, the black ket vector. This is the color basis. So the question is, how do we change from the color basis to the hardness basis? And how we're going to do that is pretty simple, and I'll show you. We are going to, and hopefully you know how to do this, and if you do, pause the video by all means and go and try to do this yourself. So, to put this in the hardness basis, what we'll do first is I'll take CW, then I'll expand the white basis vector in terms of the soft and hard basis vectors. So this is 1 over root 2 soft plus, or sorry, not plus, this is minus 1 over root 2 hard plus C black times 1 over root 2, and then this would be soft plus 1 over root 2 hard. And now if we go ahead and combine like terms, do this in orange to show we are now writing it fully in the hardness basis. So when we are doing this, well, I see, and with the coefficient on soft, I've got CW plus CB over root 2 times this soft state, right? Hopefully you see where I'm getting this. And then we have plus CB, CB minus CW over root 2 times the hard state vector. And now this is the hardness basis. And so now we have found, we can show with this that C soft, what color to write this in? I'll write it in white here. We've shown that C soft is CW plus CB over root 2, and C hard is on, remember these are going to be the probability amplitudes. We take the norm squared and we get our probability. C hard is CB minus CW over root 2. But what we've done here is we've written psi, we started in the color basis, and then we now have written it in the hardness basis. And how we did that was we used the expressions for the white and black state vectors, the white and black states, in the hardness basis. And similarly, if we started with say CS times the soft state plus CH times the hard state, we could have just used these substitutions to get back to the color basis. So hopefully this makes sense. And I'm going to erase this, and we'll see how we can use this in our what we're currently doing in section 3. So what we know from our experiments about quantum mechanics in section 1, we know that not every quantity, not every observable quantity is continuous, while position and in many cases momentum are continuous quantities, are continuous variables. They're not necessarily, not everything is necessarily continuous. For example, energy. We know for atoms, energy is very much not continuous. That's why we get those discrete spectra. So we can write a state vector, psi, in the energy basis. This is psi equals, equal sign, psi equals C1 times phi sub E1 plus C2 times phi sub E2 plus C3 plus times phi sub E3 plus dot dot dot, right? And we can express this more compactly. It's the sum over, instead of J, I'm actually going to use N. N is just more common to use for energy. It's like that principal quantum number. And so the sum over all values of N of C sub N times the state phi sub E sub N. Now, even though this looks very abstract, right, this could actually represent an actual state vector for a particle. So, for example, say we have a particle that has a 50% chance of being in the of having an energy E1, 30% chance of having an energy E2, and then 20% chance of having an energy E3. So we could write that as psi equals, well, 50% chance, so we need to take the square root of 1/2, 1 over root 2, because when we square that, then we'll get the probability. Phi sub E1 plus 1 over root 3 phi sub E2 plus 1 over root 5, right? Because then if we square that, we'll get 1/5, which is 20%, times phi sub E3. And this would be actually the full complete state vector. Even though this looks very abstract, this is just saying that I've got a 50% chance of having some energy E1, 30% chance, or sorry, not 30%. Oh, this would not be 30% chance. My bad. Hopefully you caught that. I was thinking about a third. This would be root 3/10. Yes, this would be root 3/10. Hopefully you caught that mistake. So yeah, so 50% chance of having energy E1, 30% chance of having energy E2, 20% chance of having energy E3. And I apologize about that mistake again. So if we look at this, this is our complete state. We have written the state of the particle in the energy basis. Now, it may not tell you that much, considering, you may want to know what the energies are, but this actually could tell you something. If I say I've got 3 energy levels, you don't even have to know the energy. I know the probability of it having the lowest energy, probability of having the second, probability of having that highest, that third energy. So this actually does tell you a great deal about the particle, and this is the complete function, nothing else. This is all you would need to write the state of the particle in the energy basis. Now, this doesn't tell you about where the particle is located, but it doesn't have to, because we're writing it in the energy basis. But what if we want to figure out, you know, where the particle is located? Well, now what we can do, just like how we did it before where we were taking it from the energy basis to the position basis, right? Because in the position basis, how we know where the particle is, that's writing psi of x, right? We want to figure out what psi of x is. Well, we should figure out, to do that, how to express each of these basis vectors in the x basis, in the position basis. Right, and so that's what we did before when we were trying to get from the color basis to the hardness basis. We figured out how to express these state vectors, the color state vectors, in the hardness basis, and then we put that in. So now we have to figure out phi sub e1 of x, right? This is so what we'll have to do is take phi sub e1 in the vector form, and we're going to have to figure out how to write it in the position basis. And this is actually going to be the problem that we're going to be solving in section 4. So right now, I'm not going to go too far into how we'll actually figure that out, but we will figure this out in section 4. All you know is there is some wave function, right? And remember, phi sub e1 of x is a wave function with a definite energy that represents a particle with a definite energy, e1. And so if we want to write this, right, and then we, first of all, we could write the other ones, phi sub e2 as phi sub e2 of x, right? This is writing the state with a definite energy in the position basis. It's writing it as a wave function with some position x. And then we'd write phi sub e3 as phi sub e3 of x. And so now, psi of x would be, if we just plug this in, 1 over root 2. No, didn't mean to write that. Phi sub e1 of x plus root 3/10 phi sub e2 of x plus plus 1 over root 5, 1 over root 5 phi sub e3 of x. Okay, so again, did not mean to write the ket vector. Okay, hopefully this is what I actually meant to write this time. So we have now written the wave function is a function of x. So that's how we'll get from a discrete basis. What I want you to see what we did here. We took it from a discrete basis to a continuous basis. Now, even though this still sort of resembles this, say we knew that, for example, and this is something, this will be unnormalized. We'll get to the normalization later. Not in this video, but in section 4. We'll actually see these are real. This is a real, actually, quantum problem that we'll eventually solve. So we know that phi sub e sub n is equal to the sine of n pi x. Okay? And so now we could write, and I'll do this in this light blue color, psi of x equals 1 over root 2 sine of pi x plus root 3/10 sine of 2 pi x plus 1 over root 5 sine. Now again, this is not normalized, but we'll just for sort of the 3 pi x for the more general like understanding of the situation, right? Just sort of understanding what we're doing, what our trick is. And now we have this doesn't even resemble, showing, energy 1, energy 2, energy 3. What we've done is we have replaced the functions with the definite energy with the function of x, and now we have written the wave function as a function of x. So what we've done here, I just want to reiterate, is we've taken a wave function in a discrete basis and turned it into a wave function in a continuous basis. And that's going to be a very, very important thing that we do. Right? Now, we also know, and I'm going to erase this, hopefully you have it all down. We also know in all bases, we have to have the inner product be the same. And in this, right, if you think about this as like the I hat unit vector and this is the j hat unit vector and k hat, right? This is just, a three-dimensional vector. We know how to take the inner product, the dot product, and we want these to be orthonormal. And they're orthonormal in a discrete basis. So we know that phi sub E1, or inner product with, or sorry, I'll say phi sub EM, inner product with phi sub En, has to be equal to delta Mn, the Kronecker delta, right? Because these are discrete quantities. This is not a continuous quantity. These are not continuous bases. Additionally, we know that, well, this is sort of in here, that phi sub EM is equal to 1, right? The norm squared, this is the norm squared of phi sub EM. So each of these basis states, they no longer have, they actually have to be normalizable, right? Which makes sense, because if you've got a 50% chance of being in the state with energy 1, that state should be a reasonable state, right? In the other videos, we took a superposition, a continuous superposition. You didn't actually have a probability of being in this one state. You had a probability of being in, this region, not in that one exact position. We talked about that at the beginning of section 3, why we defined it that way. Right? But this inner product has to work in all bases. So the last thing I want to show you in this video is just like this works, right? This is pretty obvious if just using, the definition of a vector, right? But if we also need to have this work in the position basis. So if we want to take this inner product, we'd be doing this. We'd have phi E star of x times phi E sub n dx of x. Right? This thing has to be equal to delta Mn. And you could actually show with those wave functions. I believe I had them written right. I did that off memory. That was just an example with the sign of n pi x. But those, I believe, actually do hold. They're not, again, not normalized, but I believe they are orthogonal. It might be 2 n pi x. I don't remember. But we will see in section 4. But this is right when we're eventually, solving the Schrodinger equation, getting these wave functions, we have to make sure that they hold this orthogonality condition, that this integral is equal to 1 if these functions are the same, right? They have to be normalized functions, as well as this integral equaling 0 when the energies are not the same. And so the point of this video that I wanted to show you is that we can still have these, discrete bases even in our continuous position space, and the inner product still has to work the same, right? If these were momentum states that are continuous, this inner product would be the delta function. But in the energy basis, because the energy basis is a discrete basis, even if you're taking the inner product in position space, it's got to be the same. It's got to be the same as the discrete case would give you. I hope this is making sense. This is a very big point to show, how the inner product is the same in all bases. So hopefully that makes sense, and I will see you in the next video.